Yeah.
Okay.
Right.
Now it's
Okay. Perfect.
Yeah, these are my contents actually. These are the basic sketch. That's what I'm gonna do on. So as an introduction, as we all know very well, OpenFOAM is a safety tool, C++ based, and it's free, it's open source, and it has a rich documentary, and everyone can do every manipulation on the codes by a problem. But even though all the advantages, using OpenFOAM can be challenging for some industrial applications, which are actually highly sensitive. The reason is that the OpenFOAM shows sensitiveness, highly sensitiveness on the mesh quality. Therefore, a generalized solution strategy has been put forward to help the problems for the compressible, turbulent, external flow problems. And in these problems, the Reynolds numbers, actually flows are highly dominated with the high Reynolds numbers. And so people can do minor modifications throughout the nature of the problem or the necessity of the flow. So, but this is a starting package for these kind of problems that are proposed if you are using the scheme, highly skewed tetrahedral meshes. So actually, in OpenFOAM, some of you may know, but users are actually inherently encouraged to use low skewed mesh, like having 6 or more faces. Yes, of course, the hexahedral elements can speed up the convergence. Yes, hexa elements perfectly align along the curved geometry. But when you look at the tetrahedral meshes, tetrahedral mesh seems to be easy to complex geometries. And the other reason for being used the tetras on the industrial problems, tetrahedral mesh do not cause any distortions on the complex curvature of the geometries. That's the reason sometimes you have to require to use tetrahedral meshes. That's why I'm using the tetrahedral mesh. But as I said, solution approach can be varying. Is this starter package? So I mean, you're gonna see at the next slides that some validations, some safety benchmark cases are validating this solution procedure. And let's move on with the method. To converge simulation to get a correct result with highly skewed tetrahedral meshes, but by being the highly skewed like mesh with the skewness greater than 70 degrees. And accepted, and we have to get the second order results with second order equation schemes, and this is the solution strategy that I follow through. So there are 3 steps actually. As usual, as a usual CFP procedure, you're gonna have to start with the gradient and divergence schemes as first order, and yes, there's going to be more stability, but less accuracy, and the relative factors are taken as high. So it's actually the selective gradient scheme can be summarized as the energy, velocity, and the turbulence terms are going to be limited, except the pressure gradient. And actually, pressure term is not a convective term. That's why it shouldn't be limited. It's going to add more diffusion and integration. So we don't want this. And divergence schemes are going to select it as first order. If you have a perfect mesh, perfectly aligned to perfect orthogonal, yeah, you're going to get the correct equity result. But for most of the cases, it's not. That's why it shouldn't, at the end of the day, you shouldn't use first order scheme for divergence. Of course, as we mentioned, that tetrahedral meshes, non-orthogonal corrector should be 3 or more. So this is actually that screenshot that I took. So I just want to emphasize on these that actually I went through. So Okay. Yeah, okay, right now. And for the when we look at the gradient schemes, that we use the limiting coefficient as one. If you use the limiting coefficient as 0, you gotta get a central difference scheme. But if you use the 1, it's gonna be a total variation emission at the total variation emission region. So this is the limiter. H is on the TVD region. You gotta get a limiting factor there. So for the linear solver settings that I'm using, as you can see, there is a potential flow term. So it's showing that I initialize the flow through the potential flow with 100 iteration. And I just want to also emphasize that there is a linear solver settings with the pressure. That number of size in the process level is 10. This is also important term for if you are using the compressible and high variance dominated flows. So these are the that I want to show the sketch for the first step. So for the second step, the only changing thing is the pressure variable settings, the linear solver settings that gradient and divergence schemes remain at the first step. First, we'll do them. So narrow down the relaxation factor, as you can see. So they're gonna narrow down. So it's the basic approach, and the non-orthogonal corrector numbers increased, and it was 3, but now the number of non-orthogonal correctors is 10. But for some of the problems, if you are getting a problem with the light oscillation for the breaking, or some breaking the energy terms, you're gonna maybe increase the number. Sometimes I increase like 30 or 40. And for this slide, the only thing that so for the third step, actually now the gradient divergence schemes are around second order. So actually, I'm gonna limit the energy terms by a differential gradient limit, because in this way, while the residual convergency, residual values converge, stability also preserved. So when you use the differential gradient limit, and I experience it a lot, that's why I'm preferring it. And we switched discretization and gradient numerical schemes to second order. So as you can see from the screenshot, that's why I put here. And so now to be show the results. Before the results, that I wanna mention about some key points throughout these important points that I mentioned. We have to be careful that pressure gradient is not a convention term. Central difference should be used. And for the velocity, we have to use the limiter for the get good result with the skewed tetrahedral mesh if you are using. So you have to be careful with the tetrahedral, because for set problems, this procedure shows the performance. And point to take into consideration about the advection of the velocity and scalar fields, and the advection of the scalar field emphasized placed on boundness and accuracy, but velocity emphasized placed on accuracy. This is actually saying that in comparison with the advection of the velocity, if you are mentioning about the scalar field, that there are no case set up like linear or linear upward. So you have to commonly use the limited linear or upward schemes, as you can see from there. But the additional appearance like limited schemes like upward with less limiting effect, it suggests in that way. To add the contribution of the density correction must transonic switch through. In that way, you're gonna add the density correction terms to your linear equations. But if you use low Mach number problem, if you have a low Mach number problem, there are no actually dense oscillations. That's why you shouldn't switch through if you use transonic. The must consistency switch through, actually that means that simplex scheme that you are using. So in that way, you're gonna add the non-diagonal terms, the off-diagonal terms to the equation. That's the mass potential and differentiable slope limiter, smooth convergency. We have to use, and with it's actually documents that in non-differentiable slope limiters may have some problems, and like regions get stalled for steady-state problems, and like mean mode actually is an example for that. That's why residual stability can be preserved with the differentiable slope limiter if carefully used. So these are the examples that I want to mention. That this is the Bugra M6, the experiment carried out in 1979. It's a well-known experiment. You can see at the figure 1 the test section figure. So at the figure 2, there is a mesh along the wing section, and it has a skins up to like 78 degrees, and it's a highly skewed mesh. And I wanna give you some critical information about the mesh actually. And it has a Y plus volume like 85 and approximately 2 million bundle layers. There are 12 bundle layers were created to capture the gradient changes on the wing very well. And it has totally 4 million meshes only if you and also, if I want to mention about this experiment, it's gonna has a 100 million Reynolds number, 0.84 Mach number, with a coming angle of attack like 3 degrees. So this is the experiment that, and you can see from the reverse iteration graphs that actually each step that I'm mentioning about is changing the values. As you can see, at the end, you have to use the second order schemes because the results are changing if you see the forces graphs. So these are the actually CP distribution over the sections, and it's well conforming with the experimental values. So this is the pressure contour, which is taken from the 1 minute, okay, which is taken from the preview. So this is the well-known phenomenon. Lambda shock wave is also captured. You can see that. So this is the second experiment, and the other F6 also has a 72 degrees. So surface mesh is mesh from point phase, and volume mesh is from the flat machine. It also has a 12 boundary layer created. So highly skewed actually. So this CP distribution again well conforming as a result. So these are the actually the comparison between the experimental, which is blue box, OpenFOAM radar, and ANSYS Fluent, which is a well-known industrial safety application results. So these are shown a good comparison for the different wing sections. So this is the pressure contour. We can see that at the near side of the body and the leading edge, there is a separation bubble, and we can also emphasize this. As a conclusion, most CP distributions are mostly overlapped with the experimental studies, and it shows that high mesh sensitivity of the OpenFOAM can be handled with the proper step, and tetrahedral mesh can be used a very wide range of problems with the different complexities. So as a starter package, so I'm getting always the result, even though I have a highly skilled meshes. So this is my starter pack, and I wanna share with you. Yes, so thank you. Yes. If you use the tetrahedral mesh, maybe we can assume is a highly skewed, right? 70 degrees. The 71, 72 is skewed actually. Yes. For the tetrahedral meshes, for the volume mesh part, I use flat meshing, but for the surface mesh, I get used from the pointwise. Okay. It's pointwise. Okay. Yeah. I export that and okay, because I trust more for the lens. Yeah. Volume mesh. Questions?
I have one that you kind of answered in the very beginning when we were talking about the X and the X. But I mean, maybe I'm biased because I'm more familiar or more used to use X meshes. But do you really need to move to X when it comes down to like a wing or an aircraft? Or
no. Of course, maybe for this kind of X, I use for wing or the other F6 aircraft because these are well-known benchmark cases, has experimental values. But for some problems, hexagonal meshes, using the hexa meshes can be difficult. So you inherently encouragingly use the tetra meshes. So it's easy because the distortion is gonna be low if you use the tet meshes. But of course, I wanna use the more face meshes.
I was thinking more for internal flows than external flows, perhaps, that you will have more problems, with the X meshes if you're working with a complicated geometry that is like inside something. But if you're working with external flows, I would say that would maybe have bias, but that with an X mesh you're kind of fine.
Yeah,
of course, there would be the transition between the surface and the bottom. But
if you haven't an option like a updated version of the Flint or something as safety program, we are using the previous versions. So at that versions, you don't have a hexa mesh skills. So you may have only the option to tet meshes.
Okay. So you think it's more the workflow that you used to.
That's the reason why I'm biased to tet meshes.
Okay.
It's old fashioned.
I have a question about gradients.
Yeah.
So, what's your opinion on Gauss gradients for this extended standard?
What's the second one for it? Extended?
Extended standard. So, when you not only consider neighbor cells, but also cell connection, for example, brain curves.
Yeah. So there will be, I didn't actually go from schemes, but I guess the whole strings. Yeah.
You can consider this.
Actually, I have tried when I get it for it now. I have a manage. Get it for it now. Maybe after all the information that all the experience that I go through, maybe I can get enough, but I haven't.
Because in our experience, it's squared and
For the patterns. Yeah, on forums, everyone saying that this experience preserve shows good performance on patterns, but I have this. It's not good. Okay, well, thank you again.
Hello everyone, welcome to the afternoon session of the conference. My name is Bugra Batan. I am working as a CFD engineer in the Turkish aerospace for more than 2 years. Today I will introduce our study about parametric aerodynamic shape optimization. We conducted this study together with my colleagues from the Turkish aerospace and the Dr. Çalışır from the Gazi University. This presentation consists of 5 sections. I will introduce you to motivation of the study and the brief introduction. After that, I will explain each component of the optimization framework one by one. Finally, I will tell you about the results and conclusion. You can see in this slide the evolution of commercial airliners over the last 8 years. Main purpose of this evolution is to design new aircrafts which are more aerodynamically efficient and give lower emissions and noise and have higher load capacity. According to this, intensive optimization efforts must be given for an aircraft design. Therefore, the main objective of the study is to design an open-source, computational fluid dynamics-based, parametric aerodynamic shape optimization framework. Let's have a look at an overview of the optimization cycle. The aerodynamic shape optimization cycle basically consists of 4 steps. In the first step, parametric modeling and surface mesh generation are done. In the second step, volume mesh generation. And now we are ready to CFD analysis. And in the last step, optimization process is being held. And in the present study, the optimization framework is used to optimize the N2A extent hybrid wing body. I will explain each step of the cycle further slides in details. The diagram in the upper right corner shows us which step we are at in the optimization cycle. Here we are using OpenVSP for creating parametric model of aircraft. It's quite flexible tool. You can easily design an aircraft. The good thing about OpenVSP is it's capable of generating good quality surface meshes. When the surface mesh is ready, we are using Sumo and Tetcan to build a volume mesh on top of it in each evaluation. Here you can see the input file and the details of the volume mesh. Now we are starting to CFD analysis. The table shows the open source design tools used in the CFD model. About the CFD analysis, we are only using open source tools for pre-processing and the post-processing. Here is the numerical details of the CFD simulation. We are doing steady state analysis with the given numerical settings. Here you can see the flow conditions and the boundary conditions. Just making sure our mathematical model is correct. We did a validation study and compare aerodynamic coefficients with the Boeing CFD results. Given results are compared in the polar diagram. You can see the polar diagram for different angles of attack at the cruise speed at 0.8 Mach. Since the flight conditions are in the transonic regime, we directed the same analysis with using Euler approach. You can see the result on the right side. The results are similar to the reference study. If we look at the pressure distribution on the aircraft, on top you can see the Navier-Stokes results and below the Euler results. You can see both approaches are very similar to each other. To reduce the computational cost of optimization, we will continue with the Euler approach. Up to this point, the first 3 steps of the cycle are completed. The next step is the optimization process. In the optimization study, the lift-drag ratio is set as the objective function. We are using Dakota to maximize the lift-drag ratio of the aircraft. I want to briefly talk about optimization. It's a process where you have the design variables, objective function, and constraints. The main purpose of the optimization is maximize or minimize of your objective function by changing the design variables within their limits subject to the predetermined constraints. Here we are using optimizer as Dakota, which is working like a black box model. As you can see, we are giving inputs and we are getting only outputs. Here you can see the geometrical constraints related to aircraft geometry. We have a wingspan, twist angle, sweep angles. You can see the range of the design variables in the table and also geometric representation of design variables in the figure. In total, we have 9 design variables are used in the optimization process. Before we start the optimization process, we are doing a design of experiment just to get better initial conditions for design variables. The design space exploration is done by using the Latin hypercube sampling method. This method is used to best represent the design space, and it can be defined as an optimization problem where we try to maximize the distance between the sample points. After we done 800 evaluations with using Latin hypercube sampling, we are obtained design 1, an improvement of 4.8% in the lift-to-drag ratio by increasing the lift coefficient and decreasing the drag coefficient. You can see the details in the table. In the optimization process, we are using gradient-free optimization algorithms. Each population created by the genetic algorithm represents a chromosome, and each chromosome comprises genes, and each gene represents as design variables. Genetic algorithm performs basically 4 actions to create a population. In the first step, it creates an initial population randomly, and then it performs a parent selection based on fitness, and it spawns children with the parental genes by using crossover and mutation function evaluations. In the last step, it reorders the population and eliminates the less fit to determine the new population. This cycle continues the algorithm until the convergence criteria are satisfied or the iteration limits are exceeded. Let's have a look at the details of the optimization method in Dakota. The optimization process is performed with Dakota using the single objective genetic algorithm with the given settings and the geometrical constraints. The objective function is to maximize the lift-to-drag ratio of the aircraft. The design parameters obtained from the exploration of the design space are set as the starting point in the optimization process. In the graph on the right, you can see that the solution shows convergence characteristics after 600 evaluations. As a result of 1,200 evaluation, there is a maximum relative improvement of 10%. But when the source of these improvements investigated, we selected 2 designs as example according to the variation of lift drag coefficients. We did not select the best improvement scenarios because solution is tend to create a similar like design tree geometries and a decreasing lift coefficient excessively. And let's talk about the computational time. Average time for mesh generation is 300 seconds, and time for the CFD analysis is 1,250 seconds in average. In a conclusion, one evaluation is completed in an average of 26 minutes. In this slide, I wanted to show you the more closely the initial and the optimized geometries. At the first glance, the most noticeable geometric change is the increase in the sweep angles on the fuselage and the wing. Here you can see the values of the design variables after optimization. The new designs are also compared to the original geometry in terms of volume and the surface area. Both volume and surface area increase by a maximum of approximately 5%. Here you can see the supersonic regions on the top of the aircraft in Mach contours. The supersonic region formed on the aircraft is similar for all geometries. However, when we compare with the initial geometry, it can be clearly seen that these supersonic regions are reduced in the optimized aircrafts. Except for design 3, shocks are observed on the fuselage in all other designs. However, the shock on the fuselage almost disappears in the design 1 and design 2. The reduction of the supersonic region on the aircraft and the absence of the shock on the fuselage reduce the wave drag component of the aircraft. In addition, here the pressure coefficient values are obtained in 4 different sections along the span-wise direction shown in the figure for all designs and compare with each other. You can see the highlighted sections in figures. While a stronger shock is generated in the original geometry, the shock strength was less in the sections specified in the optimized designs. This results in a reduction in the wave drag component of the aircraft. Also, we made for stability analysis for the optimized geometries. As you can see in the animation, the pitching moment coefficient is used for the nose down and the nose up motion of the aircraft. In order to say that the aircraft is stable, there must be a negative change in the pitching moment when there is a positive change in the angle of attack. Therefore, the value of the Cm alpha is expected to be negative for the stable aircrafts. You can see in the right graph, pitching moment coefficient increases negatively and the aircraft makes more nose-down pitching motion. It can be said that the new designs are statically more stable than the initial geometry. And the conclusion part, all tools used in this study are open source based, and all components of the aerodynamic shape optimization framework are interchangeable. And in optimized aircrafts, the reduction in the drag coefficients leads to an increase in the flight range. And current studies show that aerodynamic shape optimization framework is sufficiently stable and works very well. These are the references, and thank you for your kind attendance. Is there any question? Thank you.
Any questions?
If we can make it happen.
Yeah. Thanks for the talk. I don't know if you hear me.
Yeah. Can you hear the question directly from the audience?
No, the
Not really. Okay, I'll repeat it, or you can come closer. Yeah, sure.
Okay, here it comes.
Thanks for the talk. I have a question actually. Is the Dakota algorithm actually based on genetical algorithm, or it's something different?
No, it's the open source part. It's a commercial code, but some parts of it are open source. That is why we are using Dakota in the study.
No, sorry. I mean the optimization algorithm is similar to genetic algorithm.
Yes, definitely.
Okay, perfect. Yes, that was my question, and it was not clear because it was cut by the barrier in Zoom. How many generations did you need for a convergence?
600 almost.
600 generation. Okay, Thanks.
Thank you.
Questions?
Could you expand on the total cost of that then, if it's 600 generations and several minutes per flow solve?
Sorry, can you repeat again?
Could you expand on the total cost of the optimization? You mentioned the cost per flow solve and per mesh generation, but what was the total cost for all of those 600 generations?
How can I say that? CPU, you are asking CPU hours or?
Sure, yeah, CPU hours.
I don't know the information now, but I can send to you.
That'd be great, thanks.
But per evaluation, it took 26 minutes. 220 core times 26 minutes will be the answer.
Okay, and then multiple flow solves per iteration.
Yes. Yes.
Thank you.
Thank you.
Questions? Okay, so thank you. Thank you again.
Thank you. Thank you for your attendance. Have a nice day, everyone.